The spine of a suspension bridge is its cable. No other component is so graceful or so apparent. And none other is so crucial to the continuing success of a long-span bridge. Making the right choices for cabling was one of the greatest challenges facing the designers of the Akashi Kaikyo Bridge.
The difficulty is that if they use traditional materials, instead of having one main 1.1 meter diameter cable on each side of the bridge, they would have to have two cables because the material was not strong enough. What the Japanese did was to develop a higher strength wire strand. It was about 12% higher than had been used in traditional cable construction for suspension bridges.
In order to increase cable strength, we reviewed the components of the cables and were able to enhance the cable strength by increasing the amount of silicone in it. The structure of the cables is seen here. It is a bundle of 127 wires of 5 millimeters in diameter. This is called a strand. 290 of these strands make up the cables for the Akashi Kaikyo Bridge, 36,000 wires.
These strands were then rolled up on tremendously large spools and then stored at the fabrication site. Now the problem becomes, how do you erect the suspension cable? The Japanese did not want to interrupt the flow of commerce, 1,400 vehicles a day through the Akashi Straits. They wanted a means of erecting the cable such that there would be absolutely no inconvenience to the commercial user of the Akashi Straits. What they did was they decided to go to something called prefabricated wire system.
With the immense reels of cables sitting at the water's edge, a unique system was needed to sling the cables across the bridge. They chose a non-invasive procedure to pull the first cable strand across the strait.
What the Japanese did was they went to these new high-tech materials, to a fiber composite material. It's called an aramid, about a 1/4 of an inch diameter cable. Very, very lightweight, very, very strong. The helicopter actually picked one end of the cable up, took it from one anchorage to the top of the tower, first tower, top of the second tower, and to the second anchorage on the Awaji Island. Other cabling was then added, pulled across the bridge, and that was repeated 290 times because there were 290 of these prefabricated wire strands in each cable.
After 290 strands were erected, we shaped them into a circular form the way it looks now. This process is called squeezing.
The mass of wires was forced into a large circular shape by the cable clamps. Once this had been done, the suspension hanger ropes could be dropped toward the roadbed area. But first, the main cable had to be protected. This too would pioneer new technologies. The huge bundle would be wrapped in yet more steel wire by a special machine that worked tirelessly, like a metal spider. But with the covering over the wire, it was now subjected to the principal enemy of all suspension bridges, corrosion.
That's the big problem, that you don't really know what's going on in the interior. If we have enough wires then corroding and breaking, then it could potentially lead to a collapse of the bridge.
To combat corrosion, the Akashi Kaikyo Bridge uses two unique lines of defense.
This was the first time we wrapped rubber around the suspension cable. And since rubber is intolerant of ultraviolet rays, we painted the rubber to protect it. The paint was a special blend and a kind that would adhere to rubber.
This sealed the cable bundle against light, wind, moisture, and dirt. But inside the jacketed cable, almost 20% of the total area was still just empty air. How could they keep the inside of the cable dry?
Typically what's done on suspension bridges is a very heavy paste is literally spread over the wires, injected in the wires, and it would tend to fill that 20% of the voids. The Japanese wanted to control the humidity because in the absence of humidity, you can control corrosion. They decided that they would design a dehumidification system for those cables. They would pump air, dry air, throughout the whole main cable, which extends more than 4 kilometers from anchorage to anchorage.
This air must be pumped throughout the main cables 24 hours a day, every day of the year. In this, even more so than with other aspects of the bridge, maintenance is critical.
Inspection of the cable is not easy. We check the cable by using some kind of thermometer and humidimeter. We always checking inside of the cable, keep the relative humidity under 40%.
And this is really kind of unique and ingenious, because if corrosion of those cables can be controlled, that will be tremendous savings to the public 75 years, 100 years, 150 years down the line, when these cables typically start seeing corrosion-related problems.
The cables were strung the length of the bridge and then tied into the anchorages. Deep inside the anchorage tower is a receiver frame for the cable strands, which are affixed one at a time.
We did not fasten all 36,000 lines in one spot. We placed a socket at the end of the strand, so each socket is fixed separately on the anchorage.
This was repeated 290 times for each cable on each side. As one might expect, security is higher here than at any other site on the bridge. With the towers erected and the cables slung from one anchorage to the other, all that remained was to build the roadbed. But nature had one final deadly challenge to the completion of the Akashi Kaikyo Bridge, one that could bring about total destruction. January 17th, 1995. Kobe, Japan is shattered by a magnitude 7.5 earthquake. By evening, 5,000 people are dead or missing. 26,000 are injured, and the city is in flames. 1/6 of the population is homeless. And in the channel, straddling the city-killing fault, is the Akashi Kaikyo Bridge.
The actual fault went right underneath the bridge. The tower on the Kobe side stood firm. The tower on the Awaji Island side actually moved some 0.8 meters towards Awaji Island, and the anchorage on Awaji Island itself moved 1.2 meters.
The type of fault that we're dealing with is a strike-slip fault, where it's a vertical gash into the earth where one side is moving horizontally past the other side. In this particular case, there seems to have been actually two individual strands of the fault, one that ran into the interior of Japan through Kobe, and then another strand that ran out into Awaji Island. And those two strands more or less come close to each other right beneath the bridge. The epicenter of the earthquake, where the rupture actually started, seems to have been right beneath the bridge.
After the major rescue efforts were complete, attention turned to the Akashi Kaikyo Bridge. All the tests had been based on a magnitude 8.5 quake, some 100+ miles inland, but it had never been tested for a quake originating directly beneath it. Had the caisson sunk into the gravelly seabed? Had the towers, now almost 4 feet displaced, been damaged? Could they complete the bridge at all? A thorough inspection showed the bridge structure and cable to be sound. Amid the chaos and destruction of Kobe, this was welcome news. Construction continued anew a month after the earthquake. In February of 1995, it was time to install the roadway. This too would be accomplished in sections like the tower modules. Each section was prefabricated on land and staged near the bridge. The truss for the body of the bridge had been carefully designed and tested for many years via both computer and wind tunnel. Aerodynamics were a major concern because the truss work, more than any other element in the bridge, would be susceptible to the effect of winds.
A lot of the wind tunnel
tests have been carried out to measure the aerodynamic forces for evaluation of the flutter instabilities.
In fact, the government built some of the largest wind tunnels in the world, north of Tokyo, specifically to test the effects of high winds on the Akashi Kaikyo Bridge. A 1/100th scale model was used.
Keep in mind this bridge is 4 kilometers long, so you're looking at about a 40-meter model long. And they actually put this into a turbulent wind generator, and they tested that bridge in scaled wind flow up to, I believe it was 80 meters a second.
They learned that the Akashi Kaikyo Bridge could bow sideways almost 100 feet before experiencing significant damage. And to do that, the wind would have to be blowing at nearly 200 miles per hour, an unlikely scenario. The design selected for the roadbed, decking, and truss was a cantilevered truss girder. Construction of this last major phase of the bridge began in mid-1995.
The roadbed and the girders are built from the towers out, so that small sections of truss would be brought out, would be put into place, and then the suspender ropes would be attached to that particular panel of truss. Once that panel of truss was then suspended by the suspender cable, they would move on to the next section and bring another truss element out and cantilever off of the previously erected truss segment.
The open girder design was selected to afford great strength without impeding wind flow. The roadbed came next. As the bridge neared completion, the now familiar shape took form.
On top of the truss system, then, you have to place a deck. And basically what that is a steel plate. You come back in and you put a couple of inches of a special kind of asphalt right on top of the steel plate, and you put another couple of inches of a certain type of epoxy asphalt on top of that.
On April 5, 1998, the massive project was complete. 10 years and nearly $4 billion had gone into the effort. There had been 6 injuries, but because of extensive safety precautions, no fatalities. This impressive safety record stands as a testament to the efforts of the many companies whose fortunes rode on the Akashi Kaikyo Bridge. By mid-morning, the bridge opened for traffic. 1,500 invited guests were joined by tens of thousands of people from all walks of Japanese society.
I had the opportunity to be at that opening ceremony with the Crown Prince and Princess, and it was an exhilarating experience in just looking at the culmination of probably 30 years worth of work that had gone into the planning, the experimentation, the design, and finally the construction over the last 10 years.
The bridge creates a graceful sweeping arc across the Akashi Strait today. But the Akashi Kaikyo Bridge may be one of the last huge metal suspension bridges made. As the primary ingredient, steel reaches the limits of its strength.
That bridge is designed so that 90% of the weight of the bridge supports itself, which means that only 10% of the total weight of the bridge is dedicated to supporting the traffic. Previously, suspension bridges have been designed to accommodate about 25%.
A much longer bridge made of steel would be completely ineffective and could eventually collapse under its own weight.
Clearly, we need to look for stronger and lighter materials since we are chasing primarily the self-weight of the bridge to achieve longer spans.
But for now, the Akashi Kaikyo, part of a vanishing breed of heavy steel bridges, is a lone sentinel, holding the world's record for the longest single span. It stands astride the gateway to Asia, like a portal to the future. It is the pride of Japan, the Akashi Kaikyo Bridge.